Hi, I'm Léo Andrès. I'm an engineer working at OCamlPro, and today I'm going to present you our work on cross-language bug finding and solver-aided programming using Wasm. So this is joint work with Pierre, Arthur, and Dichel from OCamlPro, and also from Felipe Marques, who is a PhD student at the University of Lisbon. So in the talk, I'm going to quickly present what symbolic execution is. Then I'm going to present OE, a WebAssembly interpreter. I'm going to explain how we made the OE a symbolic interpreter from the concrete one. Then I'm going to talk about C, C++, and Rust symbolic execution. And then I'm going to give examples of cross-language bug finding, solver-aided programming, and proof of program. And at the end, I will show some benchmarks. So I'm going to start with a small introduction to symbolic execution. So it's a technique that can be used for bug findings and also proving properties about programs, but also to implement solver-aided programming or test state generation. It can be compared to deductive verification and abstract interpretation. So the difference with deductive verification is that symbolic execution is automatic. The user doesn't have to do anything to get a proof. And it differs from abstract interpretation because it is complete in the sense that when it finds a bug, you are sure it is a bug, but it's not sound in the sense that it can miss some bugs. So the main idea is like if you have a program, you want to find which input values are going to lead to a state S. So to do this, you are going to represent input values of the programs by symbols. And then you will execute the program with expressions made of concrete values and symbols. And when you encounter a branch, you are going to explore both. And while doing this exploration, you are going to store some information about like the list of previous branches in the past condition. And when you reach a state that is interesting, you generate a model by using an SMT solver and the past condition. And this model actually corresponds to the input values leading to the state S that you are interested in. So I'm going to make a small example on a C program. So this program is going to compute the mean of two integers x and y. It does so by adding them and then dividing by 2. But it has a small check inserted. That is, if mean is lower than x, then it should not be lower than y at the same time. Otherwise, it means that something is wrong. And so you can see all the possible execution of this program depending on the value of x and y. So if mean is lower than x and it's also lower than y, then we're going to have a trap. And otherwise, the execution is going to keep on. And we gain some information about the current pass condition. And what we would like to do is to write some test harness where you use two symbols, x and y, and then run the main function using these symbols to cover all possible execution paths. And what we would like to get at the end is this result saying, oh, I found a way to get an assertion failure about this assertion. When x equals this value and y is this value, then you can reach this state. And indeed, you can have an overflow leading to this bad state. So now I'm going to present OE. So initially, it was a OCaml interpreter working on regular Wasm programs that I made to experiment during my PhD. So it has many things like a formatter, a naive optimizer, a concrete interpreter working on text or binary files. an interpreter for Wasm script, so the Wasm test suite, some stuff to validate some program and to perform some conversions. It supports many of the Wasm proposals, so mostly all of Wasm 2 except SIMD. It doesn't have the GC yet, it's still ongoing work, and it doesn't have exceptions, but it has typed function references and tail calls. So when I had this interpreter, I wanted to develop a symbolic one. So the question I was asking is like, starting from a regular concrete interpreter like this, with basically like looking at the next instruction and at the stack. So here, for instance, if the instruction is an addition and we have two integers on the top of the stack, we simply add them and put the result back on the top of the stack. And here, if the instruction is if then else, we look at the condition on the top of the stack, convert it to a Boolean, and depending on the value, evaluate either the first or the second block. So the question is, how do you get a symbolic interpreter from this? So the way to do it is to parameterize the interpreter, first to abstract on the type of values and to manipulate expressions instead, and then to abstract on the execution strategy and use a choice model. I already presented this last year, so I'm not going to talk too much about it. If you want more details, it's on in our paper published last year. So we perform parallel symbolic execution made easy. And one thing to know is like we are going to perform the exploration in parallel using OCaml5 and its multi-core abilities. So what can we do with this? So here is a simple Wasm program. So the interpreter is providing a function to create integer symbols. And here you can have a start function that is going to reach and to execute an unreachable instruction if the variable x is bigger than 5. And so if you run OESIM on this file, it's going to find for which input value the program is going to crash. So we also have a concrete interpreter and a replace subcommand to check a model provided by O. So that was basically what we had like already last year. And now I'm going to show more new things. So using this WebAssembly symbolic interpreter, we can compile a C program to WebAssembly and also perform a symbolic execution of C programs. So we provide a simple interface. So here we have two main functions implemented differently. The first one is correct and the second one is incorrect. And you can create two symbols, X and Y, and compare the results of the two functions for any input values. And you can run this simple program using the OWC command, and it's going to find a counter examples. So to do this, we reuse stdlib to implement a symbolic standard library, and we have special handling in the interpreter for malloc and free to detect things like use after free or double free. We basically did the same for C++. So here it's an equivalent program using C++ construct. In the same vein, you can do OE C++ on this program, and you get counter examples. And we also did the same for Rust. So it's once again the same ID. You have two main functions and an interface exposed by OE. And you can get one more time a counter examples. Then, once you have all of this, we get interested in doing more complex things. So one nice thing when you work at the Wasm level is cross-language bug finding. You will be able to analyze a program made of, for instance, C and Rust, compile it to Wasm, and try to find bug in it. So now I'm going to give an example of a real bug that we found. It was in the Rust standard library. So The idea is like, let's pretend you have this a code base written in C, which contains a function computing the dot product of two vectors of size 2. And you are migrating your code base to Rust. So you rewrite this function in a Rust idiomatic way using higher order iterators. But you want to be sure that this rewriting is correct. So you can basically link the two functions in the same program, compile to Wasm, and run OE on the result. And surprisingly, on this example, OE is going to say, oh, the rewriting is not correct. So when we get this result, we were a little bit surprised. We decided to have a deeper look. And here is what we found. So the C version, when using the model provided by OE, is basically going to reduce to -0 because you multiply these two values, which give -0. You multiply these two, this give -0, and -0 plus -0 give -0. But in the Rust version, everything is quite similar in the beginning until this step where you sum the two -0 here, because the sum implementation is based on an accumulator. So it starts by putting +0 in the accumulator and then add all the other elements, so -0 and -0. And then here you get +0 at the result. The reason for this is that +0 is not the real neutral element for floats. You should use -0 instead, because +0 plus -0 actually give +0. So we opened a pull request on the Rust standard library that was merged, and now the initial accumulator for sum is -0. You could think it's not really important because -0 or +0 are going to compare as equal if you use any function or any comparison function, but actually it breaks tips, so the tool used to make this slide, that was relying wrongly on this behavior. So that was an example of cross-language bug finding. But once you get a symbolic execution engine, you can also do something else than bug finding, which is a solver edit programming. So I'm going to give a small example. So this one is C++ code. So the idea is to build a polynomials and try to find its roots using a symbolic execution engine. So here you say, oh, I want to build polynomials with the numbers 1, -8, and 14 and -8 as coefficients. And here is what the constructor is going to do. It says, oh, x is going to be represented by a symbol. Then I'm building h2, h3, and the full polynomial. And then this polynomial has a root. If there is a value for each, it is equal to 0. So when you want to find which are these values, you can simply call OE assert on the negation of the properties you want to solve. And it's going to find, for instance, 4, I think. This is quite similar to what Rosette is doing for Racket, but we provide it with in a parallel way and in a multi and cross-language fashion. So we used it for many different things. For instance, solving a maze, generating a set of cards for a game named Double, to generate graphs with some properties, but also on big examples. And the biggest one is probably generating music sheets for a string quartet. So I have a small representation of this. So this is actually a music sheet that has been generated by OE on a program we wrote that is including a lot of classical harmony constraints. For instance, there is limits on the instruments range. We impose that there is no crossing between different instruments, and a lot of other constraints. And more recently, we have been interested in using symbolic execution not to perform simply bug findings, but something that looks more like a proof engine. So I'm going to start with the C language. So ACSL is a specification language for C, which allows to write function contract. So you basically write a command, you write the preconditions in the requires clause and the post condition in the answer clause. And you put this near to your function, and it can then be used in a proof framework. You can also have assertions, loop invariants, type invariants, and other things. And there is a second tool named ACSL, which basically handles a subset of ACSL, and in particular the executable subset. And starting from a contract like this, it's going to instrument the code to produce a version that contains runtime assertions. So we reuse this tool in a way in order to be able to generate code from a C program. But instead of using the ACSL runtime that works on concrete value, we wrote it to work on symbolic values. So what does it mean is that you now have a command OEC ACSL that can perform symbolic execution of code annotated by specifications by generating executable assertions. So this is described in another paper if you're interested. And once we did this on the C language, we wanted to make some kind of cross-language verification. So what we did is we decided to do something similar in Wasm. So one of my interns designed Weasel. It's basically a WebAssembly specification language using the custom annotation syntax proposal. So here, for instance, you have a function +3, and it's annotated by a contract that says that the result must be equal to n plus 3. And we implemented a code generator for it, which is still quite experimental. So starting from this function annotated, you will get a new Wasm module containing code that can check the specifications. And you can run it in our symbolic execution engine. So now I'm going to give some benchmarks that are quite old, but that are already quite good, I think. So on Wasm code, we benchmarked the symbolic execution engine on a handwritten B3 library. So we compared OE running with 24 workers, so on a 24-core machine, OE with 1 worker, and 3 others Wasm symbolic execution engine. So what we see is, like on big programs, OE24 is always going to be the better. So here it's a ratio compared to OE24. So OE with 1 worker is 14 times slower, and the other tools are between 16 to 800 times slower than us. And on average, we are like 4 times to 50 times faster than others. But not on small programs, because we pay the cost for the synchronization of the multiple workers. So on this benchmark, all the tools are always finding the bug. It's just measuring the speed at which you can find the bug. And it's quite easy bugs to find. So we have another set of benchmarks working on C code that are 1,000 programs coming from TestCon. And here, the difficulty is to actually find the bug. Most of the time, you won't find it in the allowed time. So we are comparing against CLI, which was the best ranking tool in TestConf, and Symbiotic, which was the second one amongst symbolic execution engines. So there is 1 bug per program. CLI is able to find the bug in 700 cases, OE in 600, and Symbiotic in 400. The 3 tools have a lot of timeout. But what we can notice is, like, there is around 60 cases where clear and symbiotic are going to stop the analysis and say, oh, there is no bug. OE is never going to do this because we put a lot of care into not doing any approximation. So if the program terminates, you basically have a proof that the program is correct and all the assertions are never going to be reached. So that's true on Wasm code, but when you compile C to Wasm, it's not completely true because we are only working on one of the possible representation of the program, which is the one chosen by the C compiler regarding undefined behavior. So these are all benchmarks from last summer, I think. And at the time, we had no other optimization than the multi-core exploration. So now we have new optimization, and I think we should be able to perform much better. It's simply that I didn't took the time to run the benchmarks again. So that's all. The current goals are to support Wasm GC in OE to handle Java, OCaml, and Guile, to add heuristic to the exploration to try to guide the explorations toward more interesting paths first, to have a proper symbolic system interface, probably based on WASI, to add automatic harness generation so that the user doesn't have to write test harness by hand. We would like also to explore more the test generation area that I'm not really familiar with for now, and to have a better integration of the tool with editors, because I think it's not really user-friendly for now, but it can be improved. That's all. If you have any question, feel free to ask. Thanks.
Do I understand correctly that your path enumeration is basically unbounded? So you will have timeouts if there is, for example, an infinite loop in the program?
Yeah, yeah, of course.
The part where it's cross-language is super cool. Given, you know, if you have it working for C or C++, how much work was it to make it work for Rust as well?
So actually, we had C, then Rust, and only since 3 weeks I tried C++, and it was quite easy. It's not hard at all. It's not the hard part. You basically get this for free with Wasm, so it's quite nice. What is harder? It's to provide a proper system interface. So we did it a little bit with C, but I think we are waiting on WASI to stabilize and being implemented everywhere to provide like just a WASI symbolic interface.